Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum. Dear student, today we will discuss non-stoichiometric compound of inorganic material chemistry Chem 3115, and this is our fifth lecture. Non-stoichiometric compounds. In this topic we will discuss journal, introduction, history, and some examples of non-stoichiometric compound like iron oxide, iron sulfides, palladium hydrides, tungsten oxides, and some applications of these compounds. If the ratio of all the atoms in the structure is not constant, it is called the non-stoichiometric compound. The law of definite constant proportion is not existing. All transition elements show this type defect due to the partial field of d orbital. Non-stoichiometric compound, any solid chemical compound in which the number of atoms of the element present cannot be expressed as the ratio of small whole number, sometimes called batholite compound in distinction from deltanoids, in which the atomic ratio are those of small integer. Non-stoichiometric compounds are best known among the transition element. Several of them are important as component of solid-state electronic devices like rectifiers, thermoelectric generator, photodetector, and magnet useful in high-frequency circuit. The existence of non-stoichiometric compound is related to the presence of defect in the latest structures of crystalline substances, such as the absence of ions from sites that would normally be occupied. For example, a sodium chloride crystal that lacks a sodium ion and a chloride ion is defective, but still it is stoichiometric because the number of sodium ion and chloride ion are the same. If the sodium ion site, however, is filled by a neutral sodium atom, which then gives up its valence electron to fill the chloride ion site, the crystal defect is remedied, but the crystal is now non-stoichiometric because it contains more sodium ion than chloride ions. Most non-stoichiometric compounds have compositions that are close to those of stoichiometric compound and can be expressed by such formulas as WO3 negative X, CO1 minus XO, Zn1 plus XO, in which X is a positive quantity much smaller than 1. In certain cases, apparent non-stoichiometry has been shown to result from the existence of homologous series of stoichiometric compounds, such as the series of molybdenum oxides having the formula MONO3N-1, in which the compound corresponding to N is equal to 8, 9, 10, 11, 12, and 14 are known. A true non-stoichiometric compound MOO3 negative X would show a continuous variation of x within some range of value and no discrete species would be detectable. Non-stoichiometric compound are chemical compound, almost always solid inorganic compound having elemental composition whose proportions cannot be represented by integer. Most often in such materials some small percentage of atom are missing or too many atoms are packed into an otherwise perfect lattice structures. Contrary to earlier definitions, modern understanding of non-stoichiometric compound view them as homogeneous and not mixture of stoichiometric chemical compound. Since the solids are overall electrically neutral, the defect is compensated by a change in the charge of other atom in the solid, either by changing their oxidation state or by replacing them with atoms of different elements with a different charge. Many metal oxide and sulfide have non-stoichiometric examples. For example, so stoichiometric iron 2 oxide, which is rare, has a formula FeO, whereas the more common material is non-stoichiometric with the formula Fe.950. Non-stoichiometric compound exhibit special electrical or chemical properties because of the defect. For example, when atoms are missing, the other atoms can move through the solid more rapidly. Non-stoichiometric compounds have application in ceramic, superconductive material and in electrochemical system design like battery. This shows defect in crystal structures. First is vacancy, and this is interstitial defect. This is the substitution larger atom, and these are the freckle pair and substitution smaller atom.
Non-stoichiometric compounds are chemical compounds, almost always solid inorganic compounds, having elemental composition whose proportions cannot be represented by integers. Most often, in such materials, some small percentage of atoms are missing or too many atoms are packed into an otherwise perfect latticework. Contrary to earlier definitions, modern understanding of non-stoichiometric compounds view them as homogeneous, and not mixtures of stoichiometric chemical compounds. Since the solids are overall electrically neutral, the defect is compensated by a change in the charge of other atoms in the solid, either by changing their oxidation state, or by replacing them with atoms of different elements with a different charge. Many metal oxides and sulfides have non-stoichiometry examples. For example, stoichiometric iron oxide, which is rare, has the formula FeO, whereas the more common material is non-stoichiometric, with the formula Fe 0.950. Non-stoichiometric compounds exhibit special electrical or chemical properties because of the defects. For example, when atoms are missing, the other atoms can move through the solid more rapidly. Non-stoichiometric compounds have applications in ceramic and superconductive material and in electrochemical system designs. Definition: non-stoichiometric compounds are chemical compounds having elemental composition whose proportions cannot be represented by integers. They are most often inorganic compounds, and almost always solids. In such materials, some small percentage of atoms are missing or too many atoms are packed into an otherwise perfect latticework. Contrary to earlier definitions, modern understanding of non-stoichiometric compounds view them as homogeneous, and not mixtures of stoichiometric chemical compounds. Since the solids are overall electrically neutral, the defect is compensated by a change in the charge of other atoms in the solid, either by changing their oxidation state, or by replacing them with atoms of different elements with a different charge. History. Non-stoichiometric compounds are also known as bertholides, as violators of the law of definite proportions, as opposed to the stoichiometric compounds or Daltonides. The names come from Claude Louis Berthollet and John Dalton, respectively, who in the 19th century advocated rival theories of the composition of substances. Although Dalton won, for the most part, it was later recognized that the law of definite proportions had important exceptions. Occurrence. Iron oxides. Non-stoichiometry is pervasive for metal oxides, especially when the metal is not in its highest oxidation state. For example, although wustite has an ideal formula Fe0, the actual stoichiometry is closer to Fe 0.950. The non-stoichiometry reflects the ease of oxidation of Fe2+ to Fe3+, effectively replacing a small portion of Fe2+ with 2/3 their number of Fe3+. Thus, for every 3 missing Fe2+ ions, the crystal contains 2 Fe3+ ions to balance the charge. The composition of a non-stoichiometric compound usually varies in a continuous manner over a narrow range. Thus, the formula for wustite is written as Fe1XO, where X is a small number representing the deviation from the ideal formula. Non-stoichiometry is especially important in solid, three-dimensional polymers that can tolerate mistakes. To some extent, entropy drives all solids to be non-stoichiometric. But for practical purposes, the term describes materials where the non-stoichiometry is measurable, usually at least 1% of the ideal composition. Iron sulfides. The monosulfides of the transition metals are often non-stoichiometric. Best known perhaps is nominally iron sulfide with a composition Fe. The rare stoichiometric Fe end member is known as the mineral troilite. Pyrrhotite is remarkable in that it has numerous polytypes, i.e., crystalline forms differing in symmetry and composition. These materials are always iron deficient owing to the presence of lattice defects, namely iron vacancies. Despite those defects, the composition is usually expressed as a ratio of large numbers and the crystal symmetry is relatively high. This means the iron vacancies are not randomly scattered over the crystal, but form certain regular configurations. Those vacancies strongly affect the magnetic properties of pyrrhotite. The magnetism increases with the concentration of vacancies and is absent for the stoichiometric Fe. Palladium hydride. Palladium hydride is a non-stoichiometric material of the approximate composition PDHX. This solid conducts hydrogen by virtue of the mobility of the hydrogen atoms within the solid. Tungsten oxide. It is sometimes difficult to determine if a material is non-stoichiometric or if the formula is best represented by large numbers. The oxides of tungsten illustrate this situation. Starting from the idealized material tungsten trioxide, one can generate a series of related materials that are slightly deficient in oxygen. These oxygen-deficient species can be described as WO3X, but in fact they are stoichiometric species with large unit cells with the formulas WNO, where N equals 20, 24, 25, 40. Thus, the last species can be described with the stoichiometric formula W400118, whereas the non-stoichiometric description WO2.95 implies a more random distribution of oxide vacancies. Other cases at high temperatures, titanium sulfides present a series of non-stoichiometric compounds. The coordination polymer Prussian blue, nominally Fe 718, is well known to form in non-stoichiometric proportions, and the non-stoichiometric phases exhibit useful properties vis-a-vis their ability to bind cesium and thallium ions. Applications: oxidation catalysis. Many useful chemicals are produced by the reactions of hydrocarbons with oxygen, a conversion that is catalyzed by metal oxides. The process operates via the transfer of lattice oxygen to the hydrocarbon substrate, a step that temporarily generates a vacancy. In a subsequent step, the oxygen vacancy is replenished by the O2. Such catalysts rely on the ability of the metal oxide to form phases that are not stoichiometric. An analogous sequence of events describes other kinds of atom transfer reactions, including hydrogenation and hydrodesulfurization, catalyzed by solid catalysts. These considerations also highlight the fact that stoichiometry is determined by the interior of crystals. The surfaces of crystals often do not follow the stoichiometry of the bulk. The complex structures on surfaces are described by the term surface reconstruction. Ion conduction. The migration of atoms within a solid is strongly influenced by the defects associated with non-stoichiometry. These defect sites provide pathways for atoms and ions to migrate through the otherwise dense ensemble of atoms that form the crystals. Oxygen sensors and solid-state batteries are two applications that rely on oxide vacancies. Superconductivity. Many superconductors are non-stoichiometric. For example, yttrium barium copper oxide, arguably the most notable high-temperature superconductor, is a non-stoichiometric solid with a formula represented by YXBA2Cu307-X. The critical temperature of the superconductor depends on the exact value of X. The stoichiometric species has X equals 0, but this value can be as great as 1.
Non-stoichiometric compounds have two types: metal excess defect, in which the positive of the metal become more as compared to other. For example, zinc oxide, which is white in color, and Zn2 positive, it is yellow. Zinc oxide has more inlets by removal of oxygen. Metal detecting defect. When sodium chloride crystal is heated with the sodium, the electron replaces chloride, so it becomes metal deficient. Journal examples: WO3 minus X, Fe1 minus XO, Ni1 minus XO, Zn1 plus XO, Fe1 minus XS, PDX HX, CO1 minus XO. And this is stoichiometric and non-stoichiometric compound examples like ZnO zinc oxide, which is stoichiometric and it is transparent and insulator, but when it is in case of non-stoichiometric, it is orange in color and n-type semiconductor. And the second example is nickel oxide, which is green and semiconductor, and non-stoichiometric nickel oxide, which is black and p-type doping semiconductor. Only small amount variation occur in non-stoichiometric compound. Non-stoichiometric compounds are also known as Bertholite, as violator of the law of definite proportion, as opposed to the stoichiometric compound are Daltonite. The name come from Bertholite and Dalton respectively, who in 19th century advocated rival theories of the composition of substances. Although Dalton won for the most part, it was later recognized that the law of definite proportion had important exceptions. Now we see different examples. First is iron oxide. Non-stoichiometric is pervasive for metal oxides. especially when the metal is not in its highest oxidation state. For example, although wostite, that is ferrous oxide FeO, has an ideal stoichiometric formula FeO, the actual stoichiometry is closer to Fe 0.950. The non-stoichiometric reflect the ease of oxidation of Fe plus 2 to Fe plus 3, effectively replacing a small portion of Fe plus 2 with the two-thirds their number of Fe plus 3. Thus, for every 3 missing Fe plus 2 ion, the crystal contains 2 Fe plus 3 ion to balance the charge. The composition of a non-stoichiometric compound usually varies in a continuous manner over a narrow range. Thus, the formula for wostite is written as Fe1 minus XO, where X is a small number, 0.05 in the previous example, representing the deviation from the ideal formula. Non-stoichiometry is especially important in solid, three-dimensional polymers that can tolerate mistakes. To some extent, entropy drives all solids to be non-stoichiometric, but for practical purposes, the term describes material where the non-stoichiometry is measurable, usually at least 1% of the ideal composition. In this structure, we see iron Fe plus 2 vacancy, and this is crystal defect. Next is iron sulfide. The monosulfide of the transition metal are often non-stoichiometric. Best known perhaps is nominally iron 2 sulfide, the mineral peroxide with the composition Fe 1 minus XS, where X is equal to 0 to zero point 0.2. The rare stoichiometric FeS end member is known as the mineral triolite. Peroxide is remarkable in that it has numerous polytypes, that is crystalline form, differing in symmetry, monoclinic or hexagonal, and composition. These materials are always iron deficient owing to the presence of latest defect, namely iron vacancies. Despite those defects, the composition is usually expressed as a ratio of a large number and the crystal symmetry is relatively high. And this is peroxide ore. This means the iron vacancies are not randomly scattered over the crystal but form certain regular configuration. Those vacancies strongly affect the magnetic properties of peroxide. Main, the magnetism increases with the concentration of vacancies and is absent for the stoichiometric FeS. Next is palladium hydride. Palladium hydride is the non-stoichiometric material of the approximate composition PDHX, where X is 0.022 to 0.58. This solid conduct hydrogen by virtue of the mobility of the hydrogen atom within the solid. And the next is tungsten oxide. It is sometimes difficult to determine if a material is non-stoichiometric or if the formula is best represented by large number. The oxides of tungsten illustrate this situation. Starting from the idealized material tungsten trioxide, one can generate a series of related materials that are slightly deficient in oxygen. These oxygen deficient species can be described as WO3 X but in fact they are stoichiometric species with large unit cell with the formula WNO3N-2 where N is equal to 20, 24, 25 and 40. Thus the large species can be described with the stoichiometric formula W40O118, whereas non-stoichiometric description WO2.95 implies a more random distribution of oxide vacancies. Other cases of non-stoichiometric compounds at high temperature mean 1000 degree titanium sulfide present a series of non-stoichiometric compound. The coordination polymer Prussian blue Fe7CN18 is well known to form in non-stoichiometric proportion, and the non-stoichiometric phases exhibit useful properties, mean their ability to bind cesium and thulium ions. Now applications of non-stoichiometric compound: first is oxidation catalysis. Many useful compounds are produced by the reaction of hydrocarbon with oxygen, a conversion that is catalyzed by metal oxide. The process operates via the transfer of latest oxygen to hydrocarbon substrate, a step that temporarily generates a vacancy or defect. In a subsequent step, the missing oxygen is replenished by oxygen. Such catalysts rely on the ability of the metal oxide to form phases that are not stoichiometric. An analogous sequence of events describe other kind of atom transfer reaction including hydrogenation, hydrodesulfurization, catalyzed by solid catalase. These considerations also highlight the fact that stoichiometry is determined by the interior of catalyst. The surface of catalysts often do not follow the stoichiometry of the bulk. The complex structure on the surfaces are described by the term surface reconstruction. A next application is ion conduction. The migration of atom within a solid is strongly influenced by the defect associated with non-stoichiometry. These defect sites provide pathway for atom and ion to migrate through the otherwise dense assembled of atoms that form the crystal. Oxygen sensor or lambda sensor and solid state batteries are two applications that rely on oxide vacancies. One example is the cesium oxide based sensor in automotive exhaust system. At low partial pressure of oxygen, the sensor allows the introduction of increased air to affect more through combustion. Next is the superconductivity. Many superconductors are non-stoichiometric. For example, yttrium, barium, copper oxide. The most notable high temperature superconductor is a non-stoichiometric solid with the formula YXB82Cu3O7-X. The critical temperature of the superconductor depend on the exact value of X. The stoichiometric species has X is equal to 0, but this value can be as great as 1.
Non-stoichiometric defects. The ratio of combining elements in the compound is different from that required by the stoichiometric formulae. The defects which disturb the stoichiometry of the compound are called non-stoichiometric compounds. These defects are either due to the presence of excess metal ions or excess non-metal ions. Non-stoichiometric compounds are of two types: metal excess defect, metal deficiency defect. Metal excess defect. The solids with metal excess defect contain metal ions in excess to the stoichiometric ratio. Such defect is caused due to anionic vacancies, excess of extra cations at the interstitial site. Metal excess defects due to anion vacancies. In anionic solid, an anion may be missing from its lattice site, leaving a hole which is occupied by an electron. To maintain the electrical neutrality, the anionic site occupied by an unpaired electron is called F centers, where F stands for Farbencenter, which is a German word for color center. F centers are responsible for the color of the compound. This kind of defect is shown as alkali halides, such as sodium chloride and potassium chloride. Metal excess defect due to the presence of extra cations at interstitial sites. In this type of defect, metal excess is caused by an extra cation occupying the interstitial site. To maintain electrical neutrality, an extra electron is also present in some other interstitial site. This defect is found in crystals having Frenkel defects. Example: zinc oxide is white or colorless solid at room temperature. But when zinc oxide is heated, it loses oxygen and turns yellow color. ZNO gives Zn2 plus 1/2 O2 plus 2E minus on heating. The excess Zn plus 2 ion gets trapped into the interstitial sites and the released electrons get trapped in its neighboring interstitial sites and maintain the electrical neutrality. Crystals with either of these metal excess defects contain some free electrons. Hence, such materials are semiconductors. Metal deficiency defect. This kind of metal deficiency defect is created when a metal ion goes missing from its original lattice site. To maintain the charge neutrality, same metal ion having higher positive charge is added to occupy the vacancies created in the crystal. As this metal ion has higher positive charge, it will occupy only some of the sites to balance the overall charge, and other sites will be left vacant. Example: FeO is mainly found having a composition of Fe 0.950. In crystal of FeO, if some of the Fe2 plus ions goes missing, then the loss is compensated by the addition of Fe3 plus ions. In this way, though the overall charge is balanced, some spaces will be left vacant in the crystal.
Now, this is the assignment. Why magnetic property increases as vacancies increases? Kindly solve it. Dear student, if you have any question, you can send me your question at my email ID maslamchemist@hotmail.com. Thank you so much. Allah Hafiz.